Alright guys, today we are talking about related rates. Related rates are essentially word problems that talk about how you relate different rates of change. That is, we're going to have equations where we're going to have x's and y's in the same equation, like we have seen before. Or maybe, thetas and t's for time. Or variables like height, area, base, width. So we'll have these different variables, and we're going to differentiate all of them, via implicit differentiation, like we've done in previous sections. And then we're going to compare, see what is the, what's this variable doing when this other variable is doing something else. How fast is x changing when y is changing at this fast. There's all these different little moving parts here. We're going to compare how each of them are changing in relation to each other. So these are called related rates. I will give you fair warning that a lot of times students find these very difficult, but you have to have, as long as you have a strong foundation in implicit differentiation, and then after that it's just all algebra. So we're going to use implicit differentiation. We're always going to differentiate with respect to t. And after that, it's just making sure that we plug in all this stuff we do know and solve for the one thing we don't know that we're looking for. Okay? And sometimes there's a little bit of geometry involved, or maybe a little bit of trigonometry involved, or algebra, of course, always. But let's just jump right in and see what happens. So with this first example here, we have the variables x and y are both differentiable functions of t and are related by this equation y equals x squared plus 3. Find dy dt, that is, find the change in y with respect to t when x is 1, and given that the change in x with respect to t is 2 when x equals 1. So here's a very basic example. Typically, as you can see in the second example here, we're not going to be given an equation. Okay, we're not going to be given the equation that we're working with. We have to figure it out. But here, since this is just the first example, we're given an equation that relates x and y in this case. And we're given a few pieces of information about x and y, and maybe how fast x is changing with respect to t. Now here's the first thing you always have to remember with related rates. You are taking the derivative, the implicit derivative of both sides with respect to t. So if we take the derivative of the left-hand side with respect to t, well, the derivative of y is just 1, but we're taking the derivative with respect to t, so we're left with a 1 times dy dt. So in previous exercises, we've always been taking the derivative with respect to x. Okay? Here we're taking the derivative with respect to t. So every time we take a derivative, we have to think to ourselves, is there a variable mismatch? If there is, we have to multiply by something over dt. For instance, right here, we take the derivative of x squared, we get 2x. But we took the derivative with respect to t, and that's an x term, so we have to multiply by dx dt. And of course, the derivative with respect to the derivative of 3 with respect to t is still 0. Okay, regardless of what variable you're taking it in relation to. So here is our derivative, and now once we have this derivative, we should be able to use this other information to solve for what we're looking for. So we're trying to solve for dy dt, and it says do that when x equals 1 and dx dt equals 2. Okay? So we could say that dy over dt equals 2 times, okay, they're telling us x equals 1, and dx dt equals 2. So when this stuff right here is true, this is what we get. And that's all we're doing here. And of course the answer there is 4. Now that's a very basic example. A very basic example. We were given the equation to start with. Usually finding this equation is half the battle. We differentiated both sides with respect to t. Very important. We're always differentiating with respect to t. And then after that, take the information you know. We were told that x equals 1, so we plugged in a 1. We were told that dx dt equals 2, and that allowed us to solve for dy dt right away. So dy dt equals 4. That is, y is changing at a rate of 4 when x equals 1, and x is changing at a rate of 2. Okay? Easy enough, right? So let's get a little harder. Let's make things a little harder. Let's see. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Now, I didn't produce the graph here because the graph here just shows some circles. Okay? The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Now, notice here we are not given any equation to start with. But I think we can, if we dig a little bit into our past here, we should be able to figure out the equation that we need. Because what does the context say? The context says a pebble is dropped, causing ripples in the form of, very important right here, circles. Circles, okay? So we're talking about what in regard to circles? Area. So it says, what is the rate, at what rate is the area changing? So what's the area of a circle? Well, we all know that, hopefully. Area equals what? Pi r squared. So this is the equation that we're working off of, just like this was the equation we're working off of in the first example. So here's the equation that we're going to work off now. Now, I'm going to do a little bit of erasing here. I'm going to say just A, okay? I'm not going to write area. I'll just say A equals, so that'll make my notation a little nicer. A equals pi r squared, okay? Now when I use implicit differentiation and take the derivative of both sides with respect to t, what do we get? Okay, well that's a, that's just a single, you think about it as a to the first power if you want to. The derivative would be 1 times dA dt. Okay, now remember pi is just a constant here, so think about the constant multiple rule. We can say, factor that pi out and take the derivative with respect to t of r squared. Okay, now what's the derivative with respect to t of r squared? We get the derivative of area with respect to t equals pi. The derivative of r squared is 2r. So let's go ahead and write this as 2 pi r. But we just took the derivative of an r term with respect to t, so we have to multiply by dr over dt. Anytime we take a derivative, we're always going to have to multiply by the rate of change with respect to t. So in this case, dr dt. Here on the left-hand side, we got 1, but we had to multiply by dA dt. So this is what we're working off of here. Now, we want to find the rate in change of the area. So which one of these things is the rate of change of the area? It's dA dt. That's what that means. The rate of change in A with respect to t. This term right here says the rate of change in R with respect to t. So here's what we're solving for. We just need to substitute in for everything that we know and then solve for dA dt. So let's see. We can say that the area is changing with respect to t at, let's see, 2 times pi. Now, what are we told r is? R is 4 feet. So r is 4. So substitute in a 4. And dr dt, it says when the outer ripple is increasing at a constant rate of 1 foot per second. So dr dt is the rate of change in the radius, which we're told is 1 foot per second, a constant rate. So let's see here. 2 pi times 4 times 1, that gives us 8 pi. Now don't forget our units. We are in, let's see, feet and seconds. So what kind of units are area? Area are units squared. So we have to say 8 pi feet squared per second. Square feet per second. Okay, so don't forget your units. Those are very important in this case. So again, pretty straightforward here. We just have to remember, first of all, how to find the area of the circle, or recognize we're dealing with the circles. Find the area of the circle. Use implicit differentiation. Simplify, just not even really simplify much at all, just a little bit of rearranging. And after that, make the proper substitutions. Okay? So for a lot of these type problems, you'll want to know your basic geometry, basic algebra, things, area of triangles, area of circles, area, maybe volume of spheres, volume of a cone. Sometimes you'll be given the required, a hint of the required formula. Other times you'll be expected. You'll be expected to know that how to find the area of the circle. That, we're in calculus. You're expected to know area of a circle. I would say you're expected to know the area, the volume of a sphere. You're expected to know the area of a triangle, some basic stuff like that. Pythagorean Theorem, basic trig, that kind of stuff. Okay, let's see what we have next. Oh, here we are with a volume type question. Okay, let's see here. Pretty short and sweet. Air is being pumped into a spherical balloon at a rate of 4.5 feet per minute. Find the rate of change of the radius when the radius is 2 feet. So air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Now, see this term right here, cubic feet? What would that indicate to you? Cubic units are always talking about volume. And that makes sense here because air is being pumped into a spherical balloon, so the volume is increasing at a rate of 4.5 cubic feet per minute. Now we have to recall, what is the volume of a sphere? Of course, we're assuming this is a perfectly spherical balloon. We're ignoring the fact that it might not be exactly. Most balloons you get are not perfectly spherical, but we'll say it's perfectly spherical. So what's the volume of a sphere? Okay, well, if you recall from somewhere back in a prior basic geometry class, we know that V equals 4/3 pi r squared. No, pi r cubed. I say you need to know it, then I put the wrong thing down. 4/3 pi r cubed. Okay? Now, just like before, let's differentiate both sides with respect to t. Always using implicit differentiation, differentiating both sides with respect to t. Do note that 4/3 is a constant, as is pi. So we don't have a product rule on the right-hand side. We just need to factor out the 4/3 pi and take the derivative of r cubed. So let's see. The derivative of v with respect to t is just dv dt. Okay, you get 1, but we took the derivative with respect to t, so we have to multiply by 1 times dv dt, so that's what we get. Now, here we get 4/3 pi. What's the derivative of r cubed? Well, it's 3r squared, but we have to multiply by dr dt because we're taking the derivative with respect to t. Now let's do a slight bit of simplification here. We can say that dv dt equals, let's see, the 3's cancel out, leaving us just with 4 pi r squared dr dt. Okay, so let's see here. Now, what other stuff are we given? I haven't really talked about the other stuff. Find the rate of change of the radius when the radius is 2 feet. Okay, so they're telling us here that r equals 2. Now, what is this telling us right here? What is the 4.5? It says the volume is changing at 4.5 cubic feet per minute. So that tells me that dV over dt equals 4.5. Okay, so I go back to my implicit derivative and I plug in the stuff that I know, and hopefully I'll be able to solve for what I don't know at that point. So let's see, if dV dt is 4.5, I could say that 4.5 equals 4 pi, okay, we know that r is 2, so 2 squared times dr dt, and that's nice. Now why is that super nice? Because I'm only left with one unknown. If I only have one unknown, I can pretty easily solve for that one variable. So let's see here. I just needed to essentially divide both sides by all of this. So I can get that dr dt, that is the rate in change of the radius, which I should notice here, I should double check at this point. The one leftover variable is what I'm looking for. Find the rate of change of the radius. dr dt is the rate of change in the radius. So you get 4.5. Let's see. Let's convert 4.5 to a fraction. That's 9 over 2, right? 9 over 2 times the reciprocal of all this, which would be 1 over, let's see, 4 pi times 4. So that would be, what, 16 pi? Okay. So that ends up being, what, 9 over 32 pi? 9 over 32 pi. Yeah, 16 times 2 times pi, 9 on the top. Sure, it's not a pretty answer, but I think it works. Okay, now what are the units here? We're talking about the rate and change of a radius, and we're talking about if volume is cubic feet, then we're talking about a radius being in feet. So that would be feet, and it's per minute. Feet per minute. So 9 over 32 pi, what's the decimal approximation? Now that's my answer. I'm just curious of what that number actually is. 9 divided by 32, let's see here, 32 pi. Oh, it's about 0.089. So it's not changing very fast. The radius is not changing very fast. Again, I hope you're seeing the pattern here. We need to get an equation that relates our variables. In this case, it was radius and volume. How do we relate radius and volume? Well, we have a pretty nice equation here. We then differentiate both sides, substitute in for what we know, and hopefully that leaves us with one thing which we're looking for, and we solve for it. Let's look here, a little bit harder. An airplane's flying on a flight path that will take it directly over a radar tracking station, as shown in this figure. I didn't reproduce the figure, so I'll draw it for you. Let's see what else, though. The distance s is decreasing at a rate of 400 miles per hour when s equals 10. What is the speed of the plane? All right, so I'm going to just draw a basic figure here. So there's some sort of tracking station. We'll draw the ground. I'm a terrible artist, but it'll be all right. There's some sort of radar station on the ground. Okay, and then the plane is flying directly over that radar station. Okay, so I'm not going to attempt to draw a plane, but let's just say a plane is right here. That dot is an airplane, okay? It's going to go directly over a tracking station. Now I need to show this flying in a level flight path, okay? So it's going to go directly over a tracking station. So we'll say that's just radar. Okay? Now let's see here. Directly over radar tracking station, the distance S is decreasing at a rate of 400 miles per hour. Now what the figure shows that I haven't done here is that this is the distance S that we're talking about. This distance right here, and again, this would be provided in a figure to you. A lot of times you do want to consider a picture. So we have this distance S. We'll label this distance as X, and we're given that the altitude is 6 miles. Okay? So we're given from this diagram that the altitude of the plane is a constant 6 miles. Okay, so the plane is flying level to the Earth. It's staying 6 miles above the Earth. And we're told that the distance S, this distance right here, like the hypotenuse of this triangle, is decreasing at a rate of 400 miles per hour when S equals 10. Now, we need to find an equation that relates these variables. Now, of course, if this line right here is parallel to this line, then we know this is going to be a right angle. And when you have a right angle and a triangle, what do you almost always use? Well, what we almost always use is that thing called the Pythagorean Theorem. So what does the Pythagorean Theorem say? The Pythagorean Theorem says that this side squared plus this side squared equals this side squared. So we can say that 6 squared, let's go over here. 6 squared, in case we need a little more room. 6 squared plus x squared equals s squared. Now, of course, I know what 6 squared is. That's just 36. So I can just replace that real fast. So 36. Okay? So that's the equation I'm working off of. Now let's take the derivative of both sides with respect to t. Well, the derivative of 36 with respect to t is just 0. The derivative of x squared with respect to t is 2x. But with respect to t, I have to multiply by dx dt. The derivative of s squared is 2s, but I have to multiply by ds dt since there was a variable mismatch. And there's the equation I'm working off of. Okay? Now, what are we given otherwise, and what do we need to solve for? We want to find the speed of the plane. So what's the speed of the plane? Which one of these variables is speed? Okay? I think that approximately speed here is dx dt. How fast is the plane changing? X is the trajectory of the plane here. So how fast is x changing? That's dx dt. So we need dx dt. Okay? That is what we need. Dx dt. Okay? Now, what are we given? We're given that the distance s is decreasing at a rate of 400 miles per hour. So ds dt, I said the right thing, wrote the wrong thing. ds dt equals 400 miles per hour. Well, be careful here. I think that's a negative 400 miles per hour. It's decreasing at a rate of 400 miles per hour. Distance, we're going towards the bottom left-hand corner, and that rate is decreasing at a rate of 400 miles per hour. Okay, so we know ds dt is negative 400. We know s is 10. That was just explicitly given to us. So we know there's a 2 times x. We're solving for dx dt. We know that we have 2 on the right-hand side. We know that s is 10. And we know that ds dt is negative 400. I've substituted in for everything I know currently, but look what happened. There's still 2 unknowns. I'm solving for dx dt, but I don't know what x is. Okay, so here's where we have to do a little more digging. We're considering this situation when s is 10. So if s is 10, I think we can figure out what x is. 6 is always the altitude. If s is 10, then I think we can find x pretty easily. Right? Pythagorean Theorem all over again. So we know that, let's see, x squared plus 6 squared equals 10 squared. So x squared equals what? 100 minus 36, so 64. So x equals plus or minus 8. But since we're just dealing with a length of a side of a triangle, negative 8 is not our solution, so 8. So let's go back over here, and that's the one missing piece. And we have an 8 there. So now I have one unknown, and I can solve for dx dt by essentially just dividing both sides by 16. So let's see here. I could say that dx dt, which is what I'm looking for, is, okay, we have 2 times 10, so 20 times negative 400, divided by 2 times 8, so divided by 16, and we get negative 500. Okay? Negative, now what are the units? Miles per hour. Now the one thing we have to be careful of, I just noticed, is that we just, the final question asked for the speed of the plane. But speed is always the absolute value of velocity. Okay, so in this case, the final solution is 500 miles per hour, just because of how the question was worded with speed. Okay, because speed can't be negative. Speed, the lowest speed can go is 0. Velocity can be 0, positive, or negative, but speed can at least, it has to be non-negative. Okay, so 500 miles per hour is the speed of the plane. So look for little subtleties like that, little things like that, those little simplifications you need to make at the very end. All right, let's see here. All right, this one's a little bit harder. Okay, I made sure to leave the picture in for this one because I want to visualize what's going on here. So we're talking about an engine here. So this is a cross section of an engine here, or part of an engine. Really, it's not the whole thing. One head of an engine. Okay, so we have here a 7-inch connecting rod is fastened to a crankshaft of 3 inches. The crankshaft rotates counterclockwise, so it's rotating in this direction. Okay, so as that crankshaft rotates in the counterclockwise direction, clearly it pushes this connecting rod further away, which makes this distance x change. Okay, makes it expand. Okay, but here, connected right here would be the piston. Okay, and so we're asked for the velocity of the piston when theta is pi over 3. So when you're rotating counterclockwise and you get to theta equals pi over 3, how fast is this horizontal distance changing? Okay, how fast is that horizontal distance changing? Now, we have, let's see, we have a theta, and we have two sides of a triangle. Now, one thing I do not see here is a right triangle. Now, I could create some right triangles by drawing an altitude, but I don't need to worry about that. What do we know that we can use when we have a triangle, and we know an angle, and we know two sides like so? Okay, actually, let's just say we have three sides. We know the three sides of a triangle. This is x, but we're trying to relate these variables. So we know these three sides of a triangle and an angle. How can we relate those? Well, dig back into last semester, way back last semester, and we had two things that we would use. Two things we would use when we were trying to use trig without right triangles. We had the law of sines and the law of cosines. Then here the law of cosines is going to do the trick for us. Now, what does the law of cosines say? Let me draw a picture up here. So let me reproduce this this triangle here. Let me make it a little bit bigger. So something like this, and we'll call this B, lowercase b, A, lowercase a. Remember, capital A, B, and capital C are the angles, and lowercase a, b, and c are the sides. So what is the law of cosines tell us? Remember, and that's our thetas over here. So this is the theta we're talking about. So let's do the law of sines as it relates to this angle right here. Okay? So we could say that b squared equals what? Think. A squared plus c squared. It's the other two sides squared minus 2 times AC cosine b. That's what the law of cosines tells us. We can use it to relate the three sides of a triangle and an angle. In this case, b, we'll call it theta over here. So let's see. Let's substitute into the law of cosines. Let's substitute in the stuff we know. Now, you know, I know that a lot of you guys do not remember the law of cosines, but it's one of those things you do need to remember. Law of sines, law of cosines, that stuff will pop up. You know, that stuff will pop up on occasion, especially in a section like this. So let's substitute in the stuff we know. Okay, we know that, let's see, we know b is 7. Okay, so in this case, b equals 7. A equals 3. And I'm going to say B, capital B, that's theta. And then C is, lowercase c is x. Okay, so let's see here. If we substitute in here, we would get the equation that 7 squared equals, okay, we said A was 3, so 3 squared, okay, plus C squared, well, that was x, minus 2 times A times C, so that's 3 times x, times cosine, now B, capital B is theta, so cosine theta. So let's clean that up slightly. We would say 7 squared equals 9 squared. No, not 9. Let's just go ahead. Sorry, I don't know what I'm thinking. 49 equals 9 plus x squared minus 6x cosine theta. So there's the equation that relates these items. We want to relate what we know and the variables theta, and x. Okay, so let's see here. If we differentiate both sides of this equation with respect to t, we'll get, okay, 0. The derivative of 49 is 0. The derivative of 9 is 0. The derivative of 2x is, I just told you the answer. The derivative of x squared is 2x dx dt. Oh, now we have 6x cosine theta. I should have given myself a little more room here. In fact, I'm going to back up and just do that, because that's a product rule. All right, give myself a little more room here. So the derivative of 49 is 0. The derivative of 9 is 0. Then we said 2x dx dt. Now let's factor out that negative 6. We have a product rule. We have x times cosine theta. So the derivative of the first function times the second function. So again, we're going to look at this being one function and this being one function. I factor the negative 6 out. So the derivative of x with respect to t is just dx dt times the second function, cosine theta, plus the derivative of the second function. Now, what's the derivative of cosine theta? Well, it's negative sine theta times d theta dt, because I took the derivative of a theta term with respect to t. So negative sine theta, d theta dt, times the first function, which was x. So there is the derivative I'm working with. We have some dx's, we have x's, we have cosine thetas, and we have d theta dt's. Now, what do we know from the directions? The crankshaft rotates counterclockwise at a rate of 200 RPMs, revolutions per minute. Find the velocity of the piston when theta equals pi over 3. Okay, theta equals pi over 3, that's easy enough. So let's write that down. Theta equals pi over 3. Now, let's see here. What else are we looking for? We're looking, or actually, or what were we asked to find? We're finding dx dt. Okay, so that's what we're solving for. Dx dt eventually. Now, that means we need to know theta. We know theta. We need to know, let's see, sine theta. We know d theta dt. Oh, we need to know d theta dt. Okay, d theta dt. Now, what is that asking us for? That's asking us for how fast is theta changing with respect to t. Now, we're told that it's rotating at 200 revolutions per minute. 200 revolutions per minute. So how what's that rate in terms of our radians? 200 RPMs. So if it's going around a circle 200 times per minute, how many radians is that changing per minute? How many radians are in a circle? There's 2 pi, right? So it's going 200 times 2 pi, which is 400 pi. So the radius, theta is changing at 200 RPMs, which is 400 pi, is d theta dt. Again, because we're trapped, the angle is going 200 revolutions per minute. Each of those revolutions is 2 pi, so 2 pi times 200 gives us 400 pi. Okay, so let's see. We know theta, we know d theta dt. Now, do we know what x is? Well, I think that's going to require a little bit of work off to the side. Let's just go ahead and plug in what we know, and we'll show that we're missing x. All right, so we have a 0 equals, okay, let's just leave off that 0. 2 times x dx dt minus 6 times dx dt times cosine of pi over 3 minus sine pi over 3 times d theta dt, but that's 400 pi times x. Now, I'm solving this eventually for the velocity of the piston, which is dx dt. The velocity of the piston is dx dt. That's what I'm solving for. So I want those to remain, variables, but the x's is that one last thing that's kind of pesky that, I need to figure out. Now I think where I'm going to figure that out, just like in the previous example, we use the Pythagorean Theorem, in this specific situation when, we use the Pythagorean Theorem in the specific situation when s was 10. So I think we're going to have to do that same sort of thing down here, except with the law of cosines. So let's just draw another little triangle over here. So we're considering the specific case when there's pi over 3 in that angle, but everything else is the same. 3, 7. So what is x in this case? Well, let's just use the laws of cosines all over again. So we go back over here. We could say that 7 squared equals 3 squared plus x squared minus, we said, 2 times 3 times x cosine of the angle, which is pi over 3. Okay? Let's see here. We can solve this, I think. What's cosine of pi over 3? Crickets, crickets, crickets. That's what we usually get in class. All right, cosine of pi over 3 is 1/2. Okay, so let's see. We have a 49 there equals 9 plus x squared minus 6 times x times 1/2. Okay, let's what are we going to do here? We're going to probably end up doing. We're going to have a quadratic equation. Let's see what happens. Now, if we have a quadratic equation, we're going to let it set equal to 0. So let's put a 0 right there. We're going to have x squared. Now we have 6x times 1/2, so that's minus 3x. Okay. Now, if we have a 9 over here, and we subtract 49, we get minus 40. Now, we could say that 0 equals, how does this factor? I bet this factors pretty easily. Something like that. It's a trinomial, the leading coefficient's 1. So we're looking for factors of negative 40 that add to be negative 3. What about negative 8 and 5? X minus 8, x plus 5. So if we were going to solve this quadratic equation in general, we would say that x equals 8 and x equals negative 5. But just like before, we're dealing with sides of a triangle, so this is what we're looking for. X equals 8. The side of a triangle can't be negative 5 units, so 8. So now we can go back over here, and we have found that last piece that was bugging us. So an 8 goes there, and an 8 goes there. Okay. So 8, 8, and where did I just put, erase 1? 8 there. So times 8 and times 8. Now, this doesn't look like it's going to be a pretty answer. Let's see. Oh, we still need to substitute this cosine and sine. Cosine of pi over 3 and sine of pi over 3. Okay? Let's see here. We're going to have 0 equals 16 dx dt minus 6. Oh, we should probably go ahead and expand this. Okay, this is a tough one. I didn't think it was gonna be this tough. All right, so we have 6 times all this stuff. So we're gonna have 6 times cosine of pi over 3, which we know is 1/2, times dx dt. So I just distributed 6 times this first term. Then I'm going to have minus 6 times sine of pi over 3 is root 3 over 2. Oh, sorry, we need to 6 times root 3 over 2. It is negative, so that ends up being positive. Root 3 over 2 times 400 times 8. So that's what, 3,200 pi? All right, so we have what? Let's double check that. We have 6 times cosine of pi over 3, which is 1/2 times dx dt. Then we have negative 6 times this negative term, so it's plus 6. The sine of pi over 3 is root 3 over 2. And then 400 times 8 pi gives us that 3,200 pi. Now we need to solve this for dx dt. I'm almost out of room here. So I'm going to subtract this non-dx dt term from both sides. This is very similar to the process we did in the previous section on implicit differentiation, where we want to get the dx dt terms on one side, factor, then divide. So we could say that negative, let's see, 6 root 3 over 2 times 3,200 pi equals, if I factor out a dx dt on this right hand side, I'll have dx dt 16 minus 6 times 1/2, so 3. Okay. And so I'm dividing both sides by what? I'm dividing both sides by 13. So I'm going to, let's see here. In an effort to save a little bit of space here, I'm going to say that dx dt equals, all right, so I'm going to divide this side by 13. So I'm going to have, let's see, I'm going to have on the top, I'm going to have a negative 6 root 3. Let's see. On the bottom, times 3,200 pi. And on the bottom, I'm going to have 2 times 13, which is 26. So that's my answer. Now it's clearly not simplified. Let's see if it simplifies, or how it simplifies. So I get negative 9,600 square roots of 3 times pi over 13. Yikes, that's not a pretty answer. Now let's see what that is approximately. Let's see, what is that approximately? So I say 9,600 divided by 13 times the square root of 3 times pi. It's about negative 4018. Now, that is our exact answer. That's the not very pretty, but exact answer. There's the rounded answer. Now, what were our original units? That took forever. Okay, let's see. Okay, we're talking about how fast x is changing. So x is in inches here. So then we're talking about per minute. So inches per minute. So inches per minute. Yikes, that was kind of tough. Okay, I don't use the law of cosines very often, so it takes me a little bit to to work on it whenever we have something like that. So that took a little bit of work. Okay, that's definitely one of the harder ones. Okay, So law of cosines relates our variables, take the derivative. That wasn't the hardest part, but we had to use the law of cosines again over here to find the x value that was missing. And then there was some pretty atrocious simplification, but we certainly got the answer. Cool. All right. Next, more trig. I don't think this one's as hard. Let's see. Find the rate of change in the angle of elevation of the camera shown in figure 3.4 at 10 seconds after liftoff. So here we have a lot of information down here. So we have a camera over here. It's filming a rocket launch. You know, clearly as the rocket goes up, the angle theta has to increase to keep the rocket in the viewfinder. Let's see, the camera looks like it's positioned 2,000 feet away from the rocket. We have a nice right triangle here, so that screams to me Pythagorean Theorem, trig. Yeah, we have trig involved here. So let's see, find the rate in change in the angle of elevation. So we are looking for the change in theta. Change in the angle of elevation, that right there is d theta dt. So that's what we're looking for. All right. Now, how do we relate theta and the information we know here? Namely, the rocket ship is increasing in elevation. So here's how we're going to relate theta and s. Tangent theta equals s over 2,000. Opposite over adjacent. So let's differentiate both sides of that equation, and let's figure out what we know, what we don't know, and let's go from there. So what's the derivative of tangent theta with respect to t? So the derivative of tan theta is secant squared theta, but I took the derivative of a theta term with respect to t, so times d theta dt. Okay? Now what about the right-hand side? The right-hand side, well, what's the derivative? We can factor out that 1 over 2,000 and take the derivative of s. What's the derivative of s? Oh, well, that's just ds dt. It's 1 times ds dt. So there's our derivative we're working off of. We're eventually solving this for d theta dt. So what do we need here? We need ds dt. We need the change in s with respect to t. And we need to know what secant theta is. All right, let's see here. What's ds dt first of all? Well, we're given this down here, right? We're given that the rocket is traveling upward at according to this function, 50t squared. So I think we can find ds dt really easily. Okay? ds dt, it's just the derivative of that. ds dt is what? 100t. That's easy enough. Now we notice here, we took the derivative of a t term with respect to t. So that's just business as usual, 100t. So let's go over here. We could say that secant squared theta d theta. Actually, let's go ahead and solve that for d theta dt. That's what we're trying to do. Let's go ahead and say d theta dt. If I divide both sides by secant squared, it would be like this. 1 over secant squared theta times, 1 over 2,000. Now, we already said that ds dt was 100t, so this is what we would get. But what is 1 over secant squared? 1 over secant squared, that's cosine squared. Just by your basic trig identities. Okay, then so we can just say over 2,000, that works. Times 100t. Okay, now let's see here. Time, we're told this is all happening at t equals 10. So that's just 10 goes right there. At t equals 10. So that's easy enough. So times 10. But what about this cosine theta? Well, I think we can find cosine of theta by, again, considering a triangle, the specific triangle, when it occurs when t equals 10. Okay? Let's see here. Let's draw the triangle over here. Something like this. Now we know that is 2,000. This is theta. Now what is the height when t equals 10? Well, the height's given by s equals 50t squared. So when t equals 10, s equals 50 times 10 squared. So 10 squared is 100. 100 times 50 is 5,000. So this is 5,000. I think we can find the hypotenuse, right? Let's see. Well, let's see. Is that going to be an even number or a whole number? Let's see. Is 2,000. Pythagorean Theorem says 2,000 squared plus 5,000 squared equals c squared, and no. Okay, so it's not a perfect, the hypotenuse is not a perfect square. So we just have to say, this doesn't look very nice, but the square root of 2,000 squared plus 5,000 squared. That's not a very nice hypotenuse, but it is what it is. So what's the cosine of this? What's the cosine of that angle? Well, cosine is what? What's cosine? What? SOHCAHTOA? Adjacent over hypotenuse. Okay, so let's go back over here. We could say this equals, okay, adjacent over hypotenuse. So this is going to be a not very nice looking fraction, but let's just follow with what we're doing. Let's see, cosine is adjacent, which is 2,000, over hypotenuse, which is the square root of 2,000 squared plus 5,000 squared. But it's not just plain cosine, it's cosine squared. Times 100 times 10, so let's just say times 1,000. Okay. Now that's squared. Okay, so we need to simplify this fraction. First of all, notice we have 1,000 and 2,000, so that can simplify as just a 2 on the bottom. Now we have, think about rules of exponents here. We have a fraction raised to an exponent, so 2,000 squared is on the numerator, and on the denominator we have the square root squared, so we're left with 2,000 squared plus 5,000 squared. Okay. So let's see here. I'm gonna use my calculator at this point. I need to do 2,000 squared divided by 2,000 squared plus 5,000 squared, get that answer, and divide by 2. So let's see here. 2,000 squared divided by 2,000 squared plus 5,000 squared. We get on the numerator, that's surprising, we get 4 over 29 on the numerator divided by 2. If you divide by 2, of course, we get 2 over 29. Now, what is our units here? What do we solve for? We solved for d theta dt. So what's theta? How is theta measured? It's measured in radians. And now what's our our time measurement here? It's in seconds. So that's radians per second. Okay? So 2 over 29 radians per second. That one wasn't so bad, especially compared to the previous one. The one talking about the connecting rod and the crankshaft and the engine, pistons, that took a lot more work. This one seems pretty easy compared to that. Okay, so 2 over 29 radians per second. Okay, let's see, what else do we have here? Give me more examples? Yeah, we have more examples. All right, let's see here. This is one like from your homework. At a sand and gravel plant, sand is falling off of a conveyor belt onto a canonical pile at a rate of 10 cubic feet per minute. The diameter of the base of the cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? Huh. This is interesting. Okay, so let's see here. We have a cone, and the cone is being added to. It's getting taller. Okay, so there's like a conveyor belt. It's taking. There's a bunch of. Let me draw some bad pictures. So we have like a big pile of sand over here. Then you have a conveyor belt. So you have lots of sand over here, tons of sand, big piles. Then you have a conveyor belt that's taking some sand up here. It drops it off, and then it's creating a canonical pile. So you have sand going up here, and it gets dropped off, and it's forming. Here's my really bad picture for the pile of sand. Now that looks like a triangle because I'm in 2D, but that's what's going on here. So you have the conveyor belt's taking the sand up here, it's dropping it, and it's making a canonical pile. There's my nice 2D picture for you. Okay, so that's the situation happening here. Now, what does it tell us? It tells us that the base of the cone is approximately 3 times the altitude. Now, how do you find? Okay, so we need to go here. The volume of a cone is given by this right here. Okay, volume of a cone. Now, so we start here, we say volume equals 1/3 pi r squared h. Essentially what that is you find the pi squared h is the volume of the cylinder with a base of radius r. And what you do is you find the volume of that cylinder and take 1/3 of it, and that's the volume of the cone. Okay? Now, if we went straight ahead and differentiated this, I think we could do that, but I think we're given some information here that changes that situation. It says the diameter of the base of the cone is approximately 3 times the altitude. So we need to take that into consideration. What's that telling us? Because I think that's key before we do any kind of differentiation. We're told that the diameter of the base is 3 times the altitude. So the altitude is the height. So the height, height equals, let's see, the diameter of the base of the cone is approximately 3 times the altitude. So 3 times the height equals the base. Okay? Equals, I shouldn't say base, I should say diameter. So D. 3 times the height equals the diameter. Okay, the diameter of the base of the cone is approximately 3 times the height. The height, altitude is height. Okay, but we don't really, we don't see a diameter over here, we see a radius. So I think we need to say divide that by 2, and to divide that by 2, that's radius. So I think we can say here that radius equals 3h over 2. 3 halves the height. So if we go over here, we could say that volume, we can rewrite our volume equation and say that volume equals 1/3 pi. But what's radius? That's 3h over 2 squared times h. So volume equals, let's see, 1/3 pi. That's 9h squared over 4. If you square the top and you square the bottom, times h. So volume equals what? That's a 9 over 12. So that's going to be, let's see, 3/4. 3/4 pi times h cubed. Okay? So we just simplified our volume equation to have only one variable. That's nice. If we had not done that, we would have had h's and r's. That would require a product rule, which isn't hard. We'll probably have an example here soon enough when we have a situation like that. But this one simplified pretty nicely. So now I can say I'm working with the equation dv, so the derivative of the left-hand side and the derivative of the right-hand side with respect to t. I have dv dt equals, okay, I'm going to factor out 3/4 pi. And what's the derivative of h cubed with respect to t? Well, it's 3h squared dh dt. So cleaning up that just a slightly, derivative of volume with respect to t equals 9 over 4 pi h squared dh dt. Now, what's the rest of the stuff that we're told? It says 10 cubic feet per minute is how the volume is changing. The sand is falling off a conveyor belt onto the pile at a rate of 10 cubic feet per minute. Okay? So that tells us that dv over dt equals 10. Okay, what else are we told? The diameter of the base of the cone is 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? So that tells us that h equals 15. Now let's plug in that stuff, and hopefully we only have one thing left over, which is what we're looking for. But let's just see. Derivative of v with respect to t, that's 10 equals 9 over 4 pi. We're told that h is 15, so that's 15 squared times dh dt. Is dh dt what we're looking for? I think we're good. At what rate is the height of the pile changing? So that's dh dt, exactly. Okay, so all we have to do is solve for dh dt by essentially dividing both sides by all of this stuff right here. So let's see here. 10 divided by 9 over 4 pi times 15 squared equals dh dt. Now we need to simplify that, of course. Let's see, 15 squared is 225. So 9 times 225 divided by 4 does not simplify at all. Great. So, all right, I thought that might simplify. All right, so we need to simplify this. Let's go to the right-hand side. That's terrible notation, but that's fine. We're out of room. Actually, I'll just scroll down. I don't like going like that, so let's just scroll down a little bit. So, okay, that's 10. Now this doesn't simplify all. So 9 times 15 squared gives us 2025. Oh, sorry about that. That gives us 2025 pi over 4. And then, so that's still dh dt. We're eventually getting there. And then, oh, okay, we are out of room. Sorry, can't go down any further. So this, one last little division. And we get, okay, that's 40. Not 40. What am I thinking? We do flip the denominator, and then find the reciprocal and then multiply. So that is, yeah, that's right. Sorry, I don't know what I was thinking. That is, yeah, 40 over 2025 pi. Now that does simplify, at least since they're both divisible by 5. So 40 divided by 2025. So we get 8 over 405. Pi, that is. And there we go. There is dH dt. Oh, you know what? I did not label that. 8 over 405 pi. Now, what are we talking about? The height of the pile is 15 feet, and it's height, so it's not squared, it's not cubed. The height is just feet per what? We're talking about, what was the rate up here? Per minute. 10 cubic feet per minute, so that would be per minute. The rate at which the height of the pile is changing, that is dH dt. The height of the pile changing as it relates to t is 8 over 405 pi. Okay? Now let's see, what's the decimal approximation there? That is, you know, it's approximately 0.019. So it's not, you know, 0.019 feet. Not changing very fast, okay? But the volume is not changing very fast. The volume is only changing at 10 feet, 10 cubic feet per minute. So the volume is not changing very fast. So the sand is piling on at a pretty low rate. Okay. So again, make sure to leave your solution in exact form unless you're asked to specifically to round to a certain number of decimal places. So that answer isn't, you know, the prettiest answer, but that is the exact answer. You know, don't be tempted to type this into your calculator and tell me that the answer is 0.0198. Okay. Because that is the exact answer there. Unless, of course, on a test or quiz or whatever that you are specifically told to round. Okay, let's do a few more examples. Again, we made some pretty good headway here, but let's work on a few more examples to round off the lesson.
All right, so what do we have here? A 6-foot-tall woman walks at 9 feet per second toward a street light 30 feet above the ground. What is the rate of change of the length of her shadow when she's 18 feet from the street light? At what rate is the tip of her shadow moving? All right, well, just like always, draw a picture. Let's see what we have here. Draw a picture. Think of a street light. Okay. Street light, we'll do like this. Okay. And then there is a woman 18 feet away. Well, we'll just say some distance away. Alright, so let's do like this. And here is a woman. Okay. And we're talking about the shadow, so think about shadow, light hits, and there's a shadow like this. Okay? Now the thing is, let's do a little bit of erasing. We're going to have two triangles. So instead of having, you know, a little stick figure there, consider this. We have two triangles. Okay? Now think back to geometry class somewhere way back when, and we have two similar triangles here. Okay? Similar triangles. So what do we know here? We know this is 30 feet tall. And what else do we know here? Well, it says let L be the length of a woman's shadow. Okay? So L has to go there. And X be the distance from the street light. So in order to get a related rates equation, we need to relate X and L. Okay? Here's what we can say from related triangles, from similar triangles. Now, why are they similar? They're similar because they share this angle here, and they're both right. So they're similar by angle, 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 because both the big triangle and the small triangle share this little angle here. They're both right. Now, if two angles are congruent to each other, then the third angles must also be congruent. So all three angles of these two triangles are congruent, so they're similar. Oh, I'm trying to think, what am I missing here? I haven't filled everything out. She's 6 feet tall. That's what I'm missing. I was trying to figure out what the heck I was about to do here. She's 6 feet tall. Okay? So we could say that 30 over 6 equals, okay, that over that equals x plus L over the short side. Okay? So we have this side, the two sides are similar, or this divided by this. The large side to the small side is the same thing as the large side to the small side. Okay? Now, I think we have an equation here that relates this. Now let's clean this up a little bit. Like, let's say that, well, first of all, we could say this is 5, right? We could say 5 equals x plus L over L. Then we can just multiply both sides by L, and we get 5L equals x plus L. Oh, this is going to simplify really nicely. So we get 4L equals x. That was super nice, okay? So this is our, I wasn't expecting it to be so simple. That is our related rates equation. Now let's take the derivative of both sides. If we take the derivative of both sides, we'll have, derivative of the left-hand side is 4, but we're taking it with respect to t. So we have to multiply by a dl dt. Now the derivative of x is just 1, but we have to multiply by dx dt. Okay, now what are we told? What's our given here? We're told that she is walking 9 feet per second toward the street light. So 9 feet per second. What does that tell us? Does that tell us that dl dt equals 9, or does that tell us that dx dt equals 9? Okay, I think it's the dx, because x is the distance between her and the street light. So that tells us that dx dt equals, now, okay, it's toward the street light, so -9, going toward the origin. Okay, -9. So now if we plug that in over here, we have 4 dl dt equals -9. So to solve for dl dt, just divide both sides by 4, and we get that dl dt equals -9 over 4. Okay, so I think that is the rate at which the length is changing, the length of the shadow. So the shadow is changing, dl dt, the length of that side of the triangle, that's the shadow, is changing at a rate. Now what kind of units are we in? Feet per second. So feet per second. Now this other question says, at what rate is the tip of her shadow moving? Okay, at first I was thinking that's the same question. It's not the same question. Okay, the tip of her shadow is moving with her. So the tip, as she moves toward the lamppost, her shadow is moving with her. Okay, so I think for part B, so I guess here's part A. For part B, we have to add -9 plus -9 over 4, because her shadow is moving with her. They're both moving toward the left, toward the origin over here. If we're talking about if we superimpose a coordinate system. So let's see here. That would be -9 over 4. So we need a common denominator. Let's see. So we are going to get, let's see, 36 over 4 instead of 9. So 36 over 4. Alright, so what do we get there? We get that the tip of the shadow is moving at a rate of -45 over 4. And now let's not forget units. That is feet per second. Okay? So here's another technique that's going to pop up occasionally in related rates problems, and that's similar triangles. Okay, so here we did have right triangles, but there was no mention of angles, so I would tend to stay away from trig. We didn't really have any information about this distance here, so we couldn't really use Pythagorean Theorem. So when we have a situation like that, similar triangles are usually going to do the trick for us. At least that's kind of like my third go-to. I usually look at is there any angles involved? Use trig. If there's not any angles, Pythagorean Theorem. If we're dealing in right triangles, Pythagorean Theorem is the go-to. But then if there's neither of those two, it's similar triangles, I usually give those a try. Okay, so as long as we could draw a nice diagram, get us some similar triangles, the calculus here was not hard at all. It was the setup that kind of took a little bit of thinking about. All right, so this next example here is just the classic calculus 1 related rates problem. Okay, it says we have a ladder 25 feet long leaning against the wall of a house, and the base of the ladder is pulled away from the house at a rate of 2 feet per second. Okay, so let's see. I immediately see a right triangle there. And also I see a hypotenuse. Okay, so I think the Pythagorean Theorem is going to be the way to go, at least for part A. So let's see what happens here. Let's redraw a diagram. So we have a right triangle. This is the house over here. This is the ladder. We know that's 25 feet long. That's not changing. The length of the ladder is not going to be changing this entire process. Now, we're told that we're pulling away the ladder away from the house at 2 feet per second. So let's give this triangle some side. Let's label the sides. So let's just call, they're calling this R, so let's call that R, and let's call this B for base. So we could say, since we're pulling the base away, we could call that dB over dt, and the instructions say it's being pulled away at 2 feet per second. So dB dt equals 2. Okay. Now I think our related rates equation is pretty straightforward. We could just say that b squared plus r squared equals 25 squared. Well, 25 squared being 625. Okay, so this is our equation we're working off of. Now, if we differentiate both sides with respect to t, we will get 2b, but since we're differentiating with respect to t, we have to say db dt plus 2r, again with respect to t, so we have dr dt equals the derivative of 625 is 0. Okay? Now, we know that dB dt is 2, and we're told here how, excuse me, I guess we have to get to the question. How fast is the top of the ladder moving down the wall when the base is 7, 15, and 24 feet away from the wall? So essentially we have 3 different cases we're being asked about. We're being asked about the case, let's see here, where, let's see, base is 7. So we have this situation. We're being asked about when the base is 15 feet away from the wall. And we're being asked about the situation where the base is 24 feet away from the wall. Okay? So we have these 3 situations here. We'll call it case 1, case 2, and case 3. And we'll have to consider each of those cases individually. Now let's see here. If we take case 1 here, let's just start substituting in what we know. We know that 2 times b, well, b in this case is 7, times dB dt, which is going to be 2 throughout this entire problem, plus 2 times r times dr. Now we're looking for dr dt. That is, how fast is the ladder moving down the wall. That's what we're looking for in part A here. So part A, we're looking for dr dt. But we're still left with this r over here. Okay? We're solving for dr dt, but we're left with this pesky r. Now the way to find r is just to consider this case right here. Okay, clearly we can use the Pythagorean Theorem to solve for r in this case. We could say that r squared plus 7 squared equals 25 squared. So r squared equals what? 625 minus 49. So what's the square root of 625 minus 49? And 24. So that works out. Oh, not r squared equals 24. R squared was 576. R was 24. So R equals 24 in this specific case. So we go back over here and say that 2 times 24 times dr dt equals 0. And now all we have to do is solve. So we have 28 over here and 48 right there. So to solve for dr dt, we say 2, we could say 48 dr dt equals negative 28. So dr dt equals negative 28 over 48. So dr dt, let's see, those are both divisible by 2 at least. 14 over 24, then divisible again, let's see. And negative 7 over 12. Oh yeah, both divisible by 4. Negative 7 over 12. Now what are our units here? We're working in feet and seconds. So feet per second. Now it does make sense that this is a negative number because we're moving down. The top of the ladder is moving down the wall. Now I won't do each one of these cases. Maybe I'll just do one more. Okay, so for part A, we still have 2 more questions to answer. Another question is, what is, let's see here, what is dr dt when this situation is going on, when the ladder's 15 feet away from the wall? So we would, working off the exact same equation over here, we're always going back here. This is where we're going back for part A, except with the different value for r and a different value for b. Okay, so if b equals 15, then we could say that r squared plus 15 squared equals 25 squared. Well, 25 squared being 625, and 15 squared being 225, so we get r squared equals 400. So r equals 20 in this case. So we go back and we start from that, from this step again, and we could say that 2 times b, okay, but in this case b is 15, times db dt, which is the base, the change in the base of that triangle, which is 2, plus 2. Now r here we said was 20 times dr dt equals 0. So let's see here. We have that's going to be what, 4 times 15 is 60. So we're going to have 40 dr dt equals negative 60. So dr dt, the rate in the change in the the change in the base of that triangle with respect to time is negative 60 over 40. So negative 3 over 2. And again, don't forget your units, feet per second. Now, if you want to solve, I'm not going to do this one here, but you do the exact same process over again. In fact, if we know that side is 24, we've already found what the other side to be. The other side has to be automatically, let's see, 7. Okay, because we already saw that 24 squared plus 7 squared equals 25 squared. So that has to be 7. And so we'll use the these two sides essentially reversed. And so the answer is going to be different, even though because the 7, the base is 24, and the height here is 7. So at any rate, that'll be really super easy to solve if you've already done these two. Now let's move on to part B. Part B says, consider the triangle formed by the side of the house, the ladder, and the ground. So we're considering this triangle right here. And we want to consider the area of that triangle. Okay? How fast is the area changing when the base is 7 feet away from the wall, when the ladder's 7 feet away from the wall? Now, we don't want to go ahead and plug in a 7 right away. We want to write the equation for area in terms of this situation right here, this diagram, differentiate, then plug in what we know and solve for what we don't know. So what's area? Okay, now we're looking for how fast the area is changing. So we can say that area A equals 1/2 B times R. One-half BR. So we're looking here for how fast the area is changing. So we're looking for dA over dt. So taking the derivative of both sides, we have dA over dt equals 1/2. Now that's two functions multiplied together, so we have to use the product rule. So we have the derivative of the first function, which is just dB dt, times the second function, so r dB dt, plus the derivative of the second function times the first. So that's b. Now what's the derivative of r? Well, it's just dr dt. So here is our implicit derivative. Now we should be able to plug in a bunch of stuff that we already know and solve for dA dt. So let's see here. dA dt is 1/2. Now what's r in this case? We're told that the base of the ladder is 7 feet away from the wall. So we've already found the situation when the base is 7 feet away from the wall. Here's that situation right there. So in that situation, we found that r was 24. Now what's dB dt? The derivative of b with respect to t, that's the same thing as it has been. It's 2. For this entire problem, dB dt is 2. So times 2 plus what's b in this case? Well, it says 7 feet away from the wall, so the base is 7. And what's dr dt in this case? Well, that's what we just found right here. Dr dt, when the base is 7 feet away from the wall, is -7 over 12. So let's see here. We have no unknowns left except for dA dt. That's what we're solving for, so we're good to go. dA dt equals, okay, we have 1/2 times what? Well, 24 times 2, that's 48, minus 7 times 7 over 12, so minus 49 over 12. And let's see, so inside those parentheses we get 527 over 12. And so 527 over 12 divided by 1/2 Get 527. Nope, sorry, not divided by 1/2, multiplied by 1/2. 527 over 24. Now, does that reduce at all? That's the question. Nope, doesn't reduce. 527 over 24. Now, we're talking about area there. That's how the area is changing. And we're dealing in feet and seconds. So area is in feet squared. So feet squared per second. Okay? So that's part B. Talking about the area of area of that triangle changing. Now let's look at part C here. Part C says find the rate at which the angle between the ladder and the wall of the house is changing, again, when the base is 7 feet away from the wall. So now we're talking about this angle up here, theta. How fast is it changing? Clearly, as the top of the ladder moves down, the base goes out. I think this angle is going to be getting bigger. That's what it looks like to me. So let's see how that plays out. Let's see here. So we could say that how are we going to relate theta? R. Now we could use B and use tangent. I think we could get away with actually just relating R, because we're told, let's see, when it's 7 feet away from the wall. Okay, we're told when it's 7 feet away from the wall, but I think we've analyzed the situation enough that we don't even have to use tangent. Typically, I would want to relate these variables, theta, R, and B, but I think we could probably just get away with, actually, let's use, if we're told stuff about B, okay? We're told stuff about B, which is the base is 7 feet away from the wall. So let's relate theta and B. That's the most concise way to do this here. Theta and B. Now we're talking about angles, so clearly trig is on the table. So theta and B, how do we relate those? Now, I was saying that I could use tangent and relate theta, R, and B, but I think I would like to leave a variable out of the equation if I could. So let's actually relate theta, B, and 25. Now, what do we know? How do we relate theta, B, and 25? Well, that's theta, opposite, and hypotenuse. So what trig function relates an angle, an opposite side, and a hypotenuse? I think that's sine. So we could say, for part C, that sine of theta equals, let's see, opposite over hypotenuse, so B over 25. Okay? Opposite over hypotenuse. Okay? Now let's see here. If we differentiate both sides, we'll get sine of theta. No, not sine of theta. What am I thinking? What's the derivative of sine? It's cosine. Cosine theta, but we have to multiply by d theta over dt. I need to make that d theta over dt equals 1 over 25 times, now what's the derivative of b? That's just db dt. Okay? So I think this is my implicit derivative I'm working off of now. So we're solving for the change in theta. So the change in theta is dB dt. So we have dB, no, not dB, d theta. What did I say that for? D theta dt. It's too early in the morning. So d theta dt equals, we could say, 1 over 25 times dB over dt times, we're dividing both sides by cosine theta, so 1 over cosine theta. I suppose I could have called that secant. Alright, so we're solving for d theta dt. We have 1 over 25, that's nice. Now what's dB dt? Well, that's 2. That's been 2 the entire time. Now what's 1 over cosine theta? What's secant theta in this particular situation. So it turns out, this is the case we're talking about here. Now, if theta is up here, okay, we're talking about when the base is 7 feet away from the wall. So we know that's 24, that's 7, that's 25. So what's cosine of theta? Okay, cosine of theta is adjacent over hypotenuse, so 24 over 5. Okay, that's cosine. So 1 over 24 over 25. Okay, but of course, I'm dividing there, so I need to take the reciprocal. So I'm going to have 1 over 25 times, actually, let's just go ahead and call that 2 over 25. 2 over 25 times 25 over 24. So those 25s cancel out, giving us 2 over 24, or 1 over 12. 1 over 12. Cool. That's a nice answer. Now, what are our units here? Well, we're talking about thetas, so it's going to be radians. And radians we're working in seconds here. So radians per second. There we are. That is a classic Calculus 1 problem. You have a ladder sliding down the house, not sure why, because it's scraping the house. But it's sliding down the house, being pulled away, and how fast is the top of the ladder moving? How fast is the area of that triangle changing? How fast is the angle changing? All that kind of stuff. Classic Calculus 1 problem. This wouldn't be a related rates lesson, a proper related rates lesson without having this type of problem here. So there we are. I would say we're done here, but I'm going to do one more example here. I should have saved that for the finale, but I did add one more here. So let's just do one more example, and then see. We'll call it a day after that. I think we've done plenty enough. All right, so let's see. A hot air balloon is 120 feet above the ground when a motorcycle is traveling in a straight line on a horizontal road, passes directly beneath it going 45 miles per hour, which is 66 feet per second. Okay? If the balloon rises vertically at a rate of 8 feet per second, what is the rate of change in the distance between the motorcycle and the balloon 10 seconds later? Okay, well, let's see here. I think this is going to be a pretty straightforward Pythagorean Theorem question, but let's see. So if we have the ground here, I'll try to draw a horizontal line. So we have the ground here. Actually, let me give myself a little more room. We have the ground. And there's a guy on a motorcycle driving. There's also a hot air balloon up here. I'm not going to try to draw anything fancy. I'm just going to draw some points. Okay, so here's a hot air balloon up here. It's traveling upwards. And we have somewhere over here, we have, let's see. Let's use purple, I suppose. Somewhere over here, there is a motorcycle. Okay, just think about the triangle that's formed in that case. We have this triangle right here. Okay, this triangle right here. So we have a hot air balloon up here. We have a motorcycle somewhere over here. And a nice triangle. Now, what are we told here? We're told that the hot air balloon is going up. So this is going up. Now, let's just call these sides A, B, and C for, a lack of creativity here, but that's all right. So let's call that C. This can be A, and that can be B. Okay? So we're told that the hot air balloon is going up at a rate of 8 feet per second. So we know that dA over dt. It's going up, so that's a positive 8. Okay, now we're told that this distance right here, it's going away from the hot air balloon. Okay, we're going away from the hot air balloon at a rate of, where are we, 66 feet per second. So we could say that dB dt is 66. We want to use the feet per second because we've used feet per second here. We can't mix units here. You wouldn't want to say 45 because that would be mixing miles and feet. You want to have everything in the same units. So 66 is what we use there. Okay. What else do we know here? 66 feet per second, 8 feet. And it tells us, okay, at this particular moment, when the hot air balloon is 120 feet above the ground, we have that situation. Oh, okay, I see where we're going here. I see where we're going. So what's happening here is that the total distance of A is going to be 120 plus something. Because at the moment where the balloon is 120, the balloon is 100. Excuse me. At the moment when the balloon is 120 feet above the road the motorcycle passes, then after that the balloon is going up. So it's going to be 120 plus something. Now we have the general equation here, from the Pythagorean Theorem. We're going to have a squared plus b squared equals c squared. And just like before, I think we're going to have 2a dA dt. I hope we're to the point now where we just automatically write that dA dt, dB dt, dC dt. So that's going to be 2b dB dt equals 2c dC dt. Now everything here is divisible by 2, so let's just call this a dA dt plus b dB dt equals c dC dt. Now, let's start thinking about stuff that we know. What are we solving for? At what rate is the change in the distance between the motorcycle and the balloon 10 seconds later? So we're actually looking for the change in c, the distance between the balloon and the motorcycle. So we're looking for dC dt. Let's note that up here. Change in distance here, that's dC dt. So we want to be able to substitute in for everything else here so we can solve for dC dt. Okay, well, what do we know here? We know that dA dt, that's the change here, that's given by 8. Now, what's A in this case? It's saying 10 seconds later. So 10 seconds after the motorcycle passes under here, but we're told that when the motorcycle passes under the balloon, that the balloon is 120 feet above the ground. So it's 120 feet above the ground, but it's rising at 8 feet per second. So 10 seconds later, how high has the balloon risen? At 10 seconds later, 10 times 8 feet per second, it's risen 80 feet. 80 feet plus 120 feet, so the total is 200 feet above the ground. So A is 200. Okay, just to recap, the bike passes under the balloon when the balloon is 120 feet above the road. But 10 seconds later is what we're concerned about. 10 seconds pass by and the balloon is going up 8 feet per second, so 8 times 10 is 80, plus the original 120, you get 200. So we have 200 there. What is B in this case? Well, 10 seconds later, the motorcycle is going 66 feet per second. So how far has the motorcycle traveled in 10 seconds going 66 feet per second? Well, that's just 660. And what is the rate of change of the motorcycle? Well, it's 66 feet per second. Okay, equals... Now here's where we have to do a little arithmetic off to the side, because we have to consider the situation. We have to consider the situation when I have two sides of my triangle known. I know that A equals 200. Oh, that's just a pathetic triangle. That's not much better, but sure. This tablet's kind of tough to write on. So we have 200 there. We said this was 660 there. So what is C in this situation? Okay, we have 660 squared plus 200 squared. Now I doubt that's a perfect square. No, it's not. So I'm just gonna call this. I'm gonna leave it in square root form. It's 475,600. 475,600. Okay, so that is what C equals in this specific case. So we have the square root of 475,600 times dc over dt. And now we're solving for dc dt. All I have to do is this little bit of arithmetic. So 200 times 8 would be 1,600. Oh, let's just go ahead and add these up. So 200 times 8, that's 1,600, plus 660 times 66. So that right-hand side equals 45,160. If I divide it by the square root of 475,600, I will get dc over dt exactly. So let's see, 45,160 divided by the square root of 475,600. Oh, and I get 65. This is not a nice answer. Oh, okay, this is the exact answer. Okay, now I could probably, I'm sure I could reduce this in some capacity, but I think here, looking at the directions, the original directions, I'm asked to round, so I'm just going to go ahead and round. Okay, but this is the exact answer here, just not completely reduced. So if you do this arithmetic, we get 65 point, let's see, if we round, let's say, to 2 decimal places, 48. Nope, I left off my units. So let's see here, 65.48, that is feet per second. That is really fast. Okay, I think the math works out. Feet per second, that is going, that's a lot, that is changing, I guess. Okay, so if you're going, yeah, okay, 45 miles per hour is really 66 feet per second? Yeah, I guess so. Okay, 66 feet per second. Going in this direction, and this distance here is changing at 65.48 feet per second. That's interesting, that the distance, this distance is changing at 66 feet per second, but this distance is changing at 65.48 feet per second. Alright, well, coincidence there. Cool. So there we go. So just to recap, guys, we're using a lot of Pythagorean Theorem. We're using some trig occasionally. We saw an example where we use similar triangles. The general idea here is always the same. You have to first figure out your how to relate your given variables. So that's when we use this familiar area, volume, Pythagorean Theorem, these common formulas. Sometimes it takes a little bit of ingenuity. You differentiate everything with respect to t. After that, you substitute in the stuff you do know and solve for what you don't know. Sometimes you have to do little extra diagrams over here on the side to figure out a missing piece. but it's usually nothing too crazy mathematically. It's just a matter of you remembering basic trig, basic geometry, a little bit of algebra and arithmetic. Okay, so I hope this has been helpful. I did a handful of examples. Each one's slightly different, so you just have to get practice in for looking at different ones, because usually they're not going to be too exactly the same. There'll be little variations on each other. So if you have more questions, feel free to ask. I'll always glad to help you guys out. Okay, have a good one. See you soon.